Next, exercise 7. In this one, we have two operators on our vector space V such that both of them have all their characteristic roots in the underlying field F. Then we have to prove that they are similar if and only if they have the same Jordan form. So let's see the solution. So assume two such operators. Let S and T be two operators on V such that they are characteristic roots all lie in F. Let us first suppose that they have the same Jordan form. Suppose S and T have the same Jordan form. This means that there is a basis for the vector space V in which the matrix of S is in Jordan form, and there is a basis for V in which the matrix of T is also in Jordan form, and these two are actually equal. So, or then there exist bases and W1, W2 up to Wn, assuming that our vector space is n-dimensional. It's understood, of course, that V is finite dimensional. So for this basis of V such that the matrices M1 of S, so M1 of S is the matrix of S in the first basis of S, and M2 of T, which is the matrix of T in the second basis, and these are in Jordan form. In the above bases are in Jordan form and they are equal. And M1 of S is equal to the matrix of T, M2 of T. But we also know that when two bases are involved, we can have a change of basis matrix. And this fact we know from the section on matrices. And when this happens, then you can find an invertible matrix that will give you a similarity of the two operators, two matrices actually, but then you can translate that into the language of operators. So what I am talking about is this. The specific result is theorem 632. Now, by theorem 632, there exists an invertible or regular, same meaning, operator B in our algebra such that the matrix of T in the second basis, matrix of T is in the second basis, that's how, that's what M2 of T is, equals the matrix of B in the first basis times the matrix of T in the first basis times the inverse of the matrix of B in the first basis. The fact that B is invertible implies that its matrix is also an invertible matrix by the isomorphism between operator algebra and matrix algebra. This, however, is M1 B T B inverse. Again, by that isomorphism between operator and matrix algebras. Thus, M1S is equal to M1 BTB inverse. That is, the operators S and BTB inverse have the same matrix in the first basis, but then they are identical. Excuse me. And that way we get the fact that S and T are similar. This implies that S is equal to BT B inverse, i.e. S and T are similar. So that is one half of the claim. The other half is the converse. Conversely, let S and T be similar. Then by the definition of similarity, there exists, you see, let me just stop here, the proof for a moment, the solution for a moment, and let's just see that there is a possibility of confusion when we are dealing with these things now, because we are using uppercase letters to denote both operators as well as matrices. Sometimes we may make confuse between matrices and operators. Here S and T are similar as operators because they are operators, and that is why similarity, the equation that you will have for similarity, that will also involve an invertible operator, not matrix. There exists an invertible C. This C is not a matrix, but it's an operator. It's coming from the operator algebra, such that S is equal to Ct C inverse. Okay. So there exists a basis let me just put some ink. Okay, I am losing ink. Okay, so this is directly coming from our supposition that the operators are similar. Now after this, no, from that we are not going to get anything, but additionally we also of course have the fact that since the operators have all their characteristic roots lying in the underlying field, so each one of them will have a Jordan form. So next we are going to see that, and for that there will be a basis in which each operator, for each operator there will be a basis in which its matrix will be in the Jordan form. That's what we are going to next use. Now, there is a basis. Let me write the vectors as U of V in which the matrix, let me write it as M3 of T of the operator T is in Jordan form. Okay, and because of this, next I am going to write something, and I leave the task of showing that whatever I am now going to write is true to you. Then this is another basis of the space in which the matrix of S will have the same form, same Jordan form. Then V has the basis this U1 C inverse, U2 C inverse, and so on, UN C inverse, in which the matrix of S has the same Jordan form. To put it more simply, in this basis, if you find the matrix of S, then that will just be this M3 of T. But then that is the other half of the claim, the converse part. So here the solution ends. And let me just end the video here itself. We could have solved more exercises because this one is a short one, but for some reason I did not get time to go through the details. I was busy with something else. But anyway, tomorrow, as usual, we have our analysis. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Room. Have a great night.